Hi, today I am going to discuss our TSC 21 paper, Learning to Find Usages of Library Function in Optimized Binaries. I am Toufique. I am a fourth year PhD candidate from UC Davis. This work was done by me, my advisor Professor Premkumar Devanbu, and Anand Ashok Sawant. Library function usage is often hard to find in optimized binaries. Optimizations transform comprehensible natural source code into something that is entirely unrecognizable. Reverse engineering or understanding the binary's behavior is a time consuming task, but a very important one because binaries can be harmful or guilty of intellectual property theft. On top of that, optimization increases the difficulties of reverse engineering tasks by making the function call inline. So in this paper, we propose a machine learning based tool that will recover the missing function call in decompiled version of the code. So let's look into the examples here. There are two code snippets. On the left, we have a source function that is written in C. On the right, we have the decompiled version of that function. In the original source function, there are 4 function calls. In the decompiled version, we can see 3 of them. That means the decompiler failed to recover one function called string copy. So our tool Funky will recover the string copy function for the reverse engineer and help them understand the behavior of the binaries well. On that goal, we propose an automatic labeling scheme to generate dataset of binaries labeled with actual function usage, and using that dataset, we train our model Funky. Our learned labeling model Funky combined with Ghidra achieves state-of-the-art performance in function call recovery task. Now I will present a complete pipeline for decompiling the binaries and show where and how Funky can help the reverse engineer to understand the behavior of the binaries well. So the complete process starts with source code. The compiler compiles the code and introduce some form of optimizations like function inlining, date co-denomination, or loop unrolling, and give us the binaries. And the binaries are the real world starting point for the reverse engineer. The reverse engineer takes these binaries, use different kind of tools like Ghidra or IDEA Hexpro, and produce assembly and decompiled version from the binaries. And this decompiled version is the pseudo-C version of the original source code, but we can see that because of function inlining, some function call are always missing in decompiled version. And in this case, Funky can help us. Funky can work on top of that decompiled version and detect some inline functions like string copy for us. In this slide, we will discuss about the function recovery with different GCC optimization level. The base level is O0 where no optimization is done to the code. Starting from O1 at higher optimization levels, the compiler applies different types of optimization, and at higher optimization level, the code structure changes substantially. There are two decompilation tools which are very popular. The first one, Hextra IDEA Pro, which is a commercial software. The second one, Ghidra, which is an open source software. Both of the tools work better at O0 and O1 optimal level, but their performance is not that satisfactory at higher optimization level. Let's look into one toy examples and see how the inline function recovery become difficult at higher optimization level. So in the left, we have original C function. In the middle, we have the decompiled version of the C code while compiled with O0 optimization level. And on the right, we have the decompiled version of the same function while compiled with O2 optimization level. If we carefully look into the original C code, there are 4 function calls. At O0 optimization level, Ghidra able to recover most of the function. It only missed one string copy. But on the right, at O2 optimization level, we can see that all the function calls are gone. The memset and string copy that were recovered at O0 optimization level cannot be recovered in O2 optimization level by Ghidra. That means at higher optimization level, the inline function recovery tasks become more difficult and the performance of the decompilation tool decreases. In this slide, I will discuss about the data generation strategies we followed for Funcree. Funcree is a high capacity deep learning model and it required a vast amount of data. However, building C projects is quite challenging and we had to follow several rules while selecting the project. So we selected the project under active development phase. We look into the commit history and kept the one which has at least one new commit in the last 6 months. We selected the project that used Travis as their continuous integration platform. We need the public build histories for building the project and Travis can provide us with that information. Finally, we selected the projects that have available build container. So we use the build container and build the project and generate data for our training. So a project that satisfied the above 3 conditions can be considered for the final training phase. And for this task, that means building the project, we use the modified version of Bugswarm. And I will discuss about the Bugswarm in the following slide. However, Bugswarm enables large-scale automated training dataset construction. And for our training, we started with 10,000 actively developed C projects after filtering for the Travis, and for the build distribution, we are left with 2,634 projects. Now I will discuss about different features of Bugswarm and how we use that tool for our data generation process. So Bugswarm is designed to reproduce buildable pairs of buggy and fixed version. For our projects, we don't need the buggy version. We only need the reproducible test passing singleton builds. So we modified Bugswarm to fulfill our needs. So this is the list of tasks that Bugswarm perform while building the project. Bugswarm identify the right Docker container that the project uses, then it download the projects into the container. After downloading the projects, it install the dependencies, I think, which is the most difficult part of building C project. And finally, the Bugswarm build the projects using a script and the Travis configuration of the project. In the last slide, we discussed about Bugswarm and showed how Bugswarm can be useful for building the projects. For Funcree, building projects is not enough. We need the decompiled version of the code with the information which functions are inline and which are not. So in this slide, we will show how Bugswarm and Ghidra can be incorporated to generate data for Funcree. We augment the Bugswarm for C-based project. The original Bugswarm implementation did not handle C. As I already mentioned, we modified Bugswarm to produce one single bit rather than the pair of builds. And after that, we use headless Ghidra to generate the decompiled version of the code from the generated binaries. Now we have two versions of the code, the original source code and the decompiled version. So we can compare both versions and see which functions are inline and which are not. So after finding the function which are inline, we will insert indelible markers in the original source code for those functions. These indelible markers cannot be removed by compiler optimization. So when we build the project again and decompile it, even though the function call will be gone, the marker will remain in the decompiled version and indicates that which functions are inline there. Now I will explain how we incorporated indelible markers to the code. There are several approaches we tried. The first approach we tried was a naive one. We tried to assign a function inline message into a variable marker1. The problem with this approach, this marker1 variable was never used in other part of the program. So when we rebuild the project, the compiler identified this statement as a redundant one and dropped it during optimization. So if we use this approach for indelible marker, when we rebuild the project and decompile again, we will not see this statement in the decompiled version anymore. So this approach did not work for us at all. The second approach we tried, we used printf function as an indelible marker and it works to some extent. But there are some issues with printf also. This printf function makes some system calls and that significantly changed the decompiled version of the code. I should mention that if we want our machine learning model succeed, we need to make sure that our both version of the decompiled code, that means the one with the marker and then without the marker, should match exactly except the marker itself, and this is not the case for printf function. Then we tried puts function, which is very similar to printf function, and it works just like the printf. I would say it was a bit better than printf. That means it made a minimal change to the code compared to printf. But the problem exists. That means puts also make system calls, and that eventually change the decompiled version of the code. Then the final approach we tried, we used a global array marker for the indelible marker, and we found that it works because compiler doesn't know what to do with this global array, so it doesn't make any change to such array. And also, since the compiler doesn't know what to do with them, it makes minimal changes to the code. So let's look into the example here. So we have two code snippets, that means two decompiled version of the code. On the left we have the version without the marker, on the right we have the version with the marker. And if we carefully looked into the snippets, they are very similar to each other. I would say they are exactly same, except with the marker one has a statement that indicates that the memset function was inline there. In the last slide, we discussed how we produce data for Funky with the information what functions are inline there and what functions are not. In this slide, we will show how much data we gathered for training and evaluation of Funky. So we have two different setups for the experiments. On the left side, we have a cross-file setup. On the right, we have a cross-project setup. In cross-file setup, we have 8,643 files for training, 270 files for validation, and 716 files for testing in 5 optimization level. On the cross-project setup, we have 8,707 files for the training, 300 files for the validation, and 617 files for the testing. Note that in cross-project setup, we don't have sufficient projects to evaluate O1 and OF optimization level. So in cross-project setup, we could not evaluate the performance of Funky on these two optimization levels. We have already generated data for Funky. Now we'll discuss about the potential approaches that can be used to train a model. So we tried transform based model. Transformer use multi-head self-attention to extract information from different part of the sequence. It's a very popular deep learning architecture and has been successful to achieve state-of-the-art performance in many downstream tasks. The second approach we tried is Roberta, which is also a transformer based approach, but Roberta needs to go through two different stages. In the first stage, that we call pre-training, we train the model with billions of unlabeled tokens to teach the model about the statistics of the languages. In the pre-training stage, we use masked language modeling, which does not require any supervised data. In masked language or MLM, we randomly choose 15% of the token and mask out them and ask the model to predict those tokens for us. Using this training objective, the model learns better embedding to represent the sequence. In the second stage, that we call fine tuning, which is very similar to the one we followed in transformer based approach. So we use the supervised data to train the model to predict inline function for us. We performed one experiment to compare the result of transformer based approach and Roberta based approach. We are also interested to see how much information is needed to make a good prediction in library function recovery task. Note that this experiment is not applicable to real scenario. In real scenario, we will not know the positions of the marker. Here we assume that we know the positions of the marker. So we tried this experiment or compared this model and with different context length. So in the left column you can see the context length there. This plus minus 3 means that for this row we take 3 lines before the marker and 3 lines after the marker and make a sequence and give that sequence to the deep learning model for the prediction task. So we tried different context length, and we also tried different evaluation criteria like top 1 accuracy, top 5 accuracy, and top 10 accuracy. And we can see that roberta based model outperform transformer based approach in all the evaluation criteria. And regarding the context length, we can see that we need at least 20 lines of information to make a good prediction in library function recovery task. From this slide, we decide to move forward with the roberta based model because it is outperforming the transformer based model by a significant margin. In the last slide, I mentioned that in real scenario we will not know the position of the marker. So we used a sliding window approach to resolve that problem. In this slide, we compare our tool with the existing ones. Note that Funcree was trained to recover the function that were missed by Ghidra. So Funcree is not directly comparable with Ghidra or Hexray. To make it comparable, we combine the result of Funcree with Ghidra and then compare them with Hexray and Ghidra itself. If we look into the table in all optimization level, we can see that Funcree together with Ghidra achieve the maximum F score in all optimization level. Not only that, they were able to recover most number of unique function in all optimization level. Let me summarize the overall contribution of this paper. Using Bugswarm, we propose an approach to build C-based project on a large scale and generate data for models like Funcree. We also found that roberta-based Funcree do really well in inline function recovery task. And when we combine Funcree with Ghidra, it outperforms Hexray and Ghidra itself on this particular task. We also found that our tools is effective at all optimization level and perform really well in inline function recovery task. Thank you so much for listening to my presentation.